Cool. So if I could choose one theme of this conference so far, it would be this. It's that code is essentially for humans. Like Roberto mentioned in his keynote yesterday, as engineers, it's not only our job to be good at solving problems, but it's also critically important that we're good at communicating the solution. By the end of this talk, I hope you'll appreciate the role that testing also plays in communicating that intent. My name is Alan. I work at a company called Segment, and I've been using Go for about 5 years, building big data systems that I've used to help inform this talk. So, how many of you have come to a new project, whether it's open source or proprietary, uh, for work or fun, downloaded it, got it building, only to realize that there are no tests? Raise your hands. Yeah, a lot of you. And for those of you who aren't raised, do you have a custom terminal prompt? Because I'm pretty sure that doesn't have tests. My point is, though, what can you tell about a program that doesn't have any tests? You can tell that it executes the code, that the instructions that it's given, but what else? How can you be sure that a program without tests actually does what the original programmer intended it to do? Tests are the means to communicate the intent of the program to your fellow engineers, but possibly, and perhaps even more importantly, future you. So why test at all? Once again, we test to communicate the intent of your program primarily. We also test to verify that the behavior of the program is what we expect it to be. And finally, almost as an aside, along the way, we also discover and fix bugs. So before we dive into this talk, I really want to reiterate or make a point of saying that engineering is fundamentally about trade-offs and understanding them. So take nothing here in this talk as hard and fast rules to follow, but instead consider what works best in your environment and the context of your organization. And finally, if your tests aren't making it easier for you to do your work, then you should really reconsider your testing strategy, because ultimately tests should save you time in the long run. It shouldn't be taking you more time to maintain the tests than to write the code. So over the next 30 minutes or so, we're going to cover, firstly, how to structure your code best for testing. Then I'm going to go over a strategy I use for writing effective test suites. And then finally, we're going to go over some neat tricks in HTTP that hopefully will make it so that this will be the last HTTP test you ever have to write. What we're not covering in this presentation, however, is basically tooling. So GoVet, GoLent, coverage, these are all very important topics that I think everybody should use in their daily workflow. They'll really save you a lot of time in the long run as well. So I encourage you, if you aren't using any of these, then please go do some research and understand them so that you can integrate them into your daily workflow. But they're not relevant to the topic of this talk today. So first off, structuring your code is the first step in really your test strategy. Without well-structured code that's easy to test, it's really going to hurt your ability to test things. So in this section, we're going to go over a few different things, starting with dependency injection. Then we'll talk about how channels relate to testing in Go. And finally, we'll talk about how interfaces relate to testing in Go. So dependency injection probably isn't new to most of you, especially if you've come from other languages that use it frequently. But I think it's important to cover because it provides a good foundation for the rest of the content of this talk. So what is dependency injection? Dependency injection, put simply, is a means to be able to input an implementation of whatever it is that you're handling into a constructor. So this could be just a struct literal, or it could be a new method. Doesn't really matter. But let's take a look at what this means. So here are some examples of dependency injection. I chose a SQL database here specifically because it's nuanced. So really quickly, what we're doing is we have a new service, and it takes a database, and we initialize it. But I chose SQL because it's nuanced. There's no such thing as a perfect abstraction, especially when it comes to SQL implementations. You've got Postgres, you've got MySQL. They've got all these different features that don't necessarily overlap or align. So in the first example, we're actually not using dependency injection at all. This is probably something you want to avoid because it ties you specifically to whatever database connection string you've hard-coded in the code. Now, obviously, that's not very flexible. So the first level dependency injection that I have here as an example is the database connection string. Now, notice here that it's just the connection string itself. So one of the benefits of just injecting the connection string is you can now enforce the actual type of the database that you're going to connect to. So if you're using features specific to Postgres, then this might actually be the best option for you for dependency injection. In the next example, we're actually injecting a generic SQL database. So this example would be ideal if you've actually got a service that can talk to multiple different databases. So if you're writing generic enough SQL that can work with both MySQL and Postgres, this might work for you. Or if you're migrating between databases. Finally, another benefit to doing a dependency injection strategy like this would be to test locally using something like SQLite. Finally, we have the most abstract version of dependency injection in which we create a new store interface which actually satisfies exactly what this service needs from the persistence layer. Now, because this one is the most abstracted, we're not actually enforcing any of the contract that is provided by the store, or let me rephrase that. We're not actually enforcing the type of database that is actually being injected. As long as whatever it is that's injected into this service satisfies that store interface, the new service will be fine. But now you're putting your trust on whoever's implementing that store interface to do it correctly. So which one you choose really depends on the situation. They all satisfy problems in different points in time. So really consider when you're going to construct your code, which one works best given the context. So here's actually an alternative to dependency injection. If you've ever tested time, you know it's kind of a pain. So because time is constantly changing, it's not easy to be able to assert exact assertions in your tests. So what we've done here is we've actually assigned the time.now method from the time package to a packaged global variable. And in our test expiration function, we can actually take that assignment, defer restoring it again so that it doesn't affect other tests because it is packaged global. And then we can assign that now func to just a func literal that returns a well-known time that we can actually run good assertions against. But I'll do this with a word of warning because now that we've introduced a package level singleton, this really prevents us from being able to easily run parallel tests. So let's look at an alternative to the alternative, which again is dependency injection. So now we've restructured our code a little bit. And instead of having a package global variable, we've written a function which accepts a now func and returns the original function signature, which can calculate the duration in the future. And now in our tests, we can actually pass in whatever exact date that we want to be able to assert against in our calc expiry function, and then run our tests normally. So these are some varying ways that dependency injection can really help you in your tests. Now, let's move on a little bit. Channels are arguably one of the best and biggest features of Go. However, I'm going to argue that it's much easier to test an API that doesn't actually export any channels and is synchronous than it is to test an API that does export channels. So when you're using channels in your API, you have to consider all of these various things when thinking about how to test it. You have to think about what sends data on the channel, who owns the channel, what is the life cycle, is it buffered or unbuffered? these all have and imply different semantics. So in my research for this talk, I actually only found 4 examples of exported channels from the standard library that aren't reflector runtime. So these examples are net and HTTP for cancellation, signal for notifications, and time, which is also notifications but has a data component because it sends the current time. Now, these are good exceptions to that rule because they have a very well-defined and narrow scope of what they support. But you won't find any other examples in the standard library where they're actually exporting channels in a way that's more complex than that. So let's take a look at some code again. So here we have a QLib, which has a type reader, and this reader type has a method called readChan. And what this does is this exports a channel of messages. And this is a pattern I've seen somewhat frequently in my time writing Go. So you go to test this, and you might start by just initializing a new reader and ranging over the channel, making your assertions on the values that you read from the channel. And this is a fine way to start. But then you remember you should probably be error handling. As good gophers, we all know that we should be checking our errors. So fortunately, this QLib exports an error channel as well. But now we have to think, well, how do we read this and deal with timeouts? Is the channel buffered or unbuffered? And all those things that I mentioned before that make it really difficult to reason about the code that we're testing. So I propose, what if we change the signature of the library to be synchronous? So now instead of reading from a channel, we've implemented a new method which appears synchronous, at least, to the consumer. So here we have read message, which returns a message and an error. You could pass in a context if you need cancellation. And this doesn't actually have to be synchronous under the hood. You can use channels and all of the fancy concurrency primitives in your QLib package. But the caller doesn't have to know that. And as someone who's consuming the API, it's a lot easier to reason about what we're getting from this single method call. So I'd ask you, would you rather test this code or the code that exports channels? And consider that when you're programming or considering exporting a channel. Another very powerful feature of Go is interfaces. And I think interfaces are one of the more complex things for new people to Go to understand. It's a very powerful feature of Go, and I can't express enough how much I like them. But I do see them frequently misused, especially for people who are new to Go. So I would argue that library authors should avoid exporting their own interfaces unless they have a strong case to do so. And program authors should instead create their own internal interfaces to express their external dependencies. And this way, it'll make it a lot easier for you to be able to express exactly what you depend on. It'll also ease your testing concerns. So I'm going to use a package here as an example, and it's a package that's actually near and dear to my heart because I've been using it for 5 years now. And I'm not choosing this package to throw shade at it. It's a very highly performant package. It was written long before there was really good, strong idioms and idiomatic Go patterns, but this package is Sarama. So I'm using it because it's a good example of how I don't think we should be designing packages anymore. So right here you can see we're scrolling through the API, which is somewhat massive. And there's nothing wrong with that. It's basically got to do with the Kafka implementation itself. It's got an interface for every method. But what it has is it exports 22 different interfaces. And because it exports all these interfaces, it provides a special mocks package just to be able to handle those interfaces for testing. However, these interfaces fundamentally have a very tight coupling to the Kafka implementation. So I ask you, what are we testing when we're actually using this mocks package? Well, we're testing our calls into the Sarama library, that they succeed. we're testing that the mock implementation actually satisfies the interface itself. We're testing that our code that depends on Sarama, but not actually without, or we're testing it without running Kafka itself, which is arguably one of the biggest reasons to use the mocks package. But we're certainly not testing the behavior of the library itself, which is, since it specifically excludes the implementation talking to Kafka. So finally, I'd like to add that this is a fundamentally fragile design pattern, exporting interfaces, because interfaces are impossible to change. You can't add a method to an interface without breaking your consumers. So let's take a look at how we handled it when we started using Sarama. So instead of using Sarama directly, what we did at Segment is we defined a new message, which has a new package rather, which defines a message type that has a key and a value of byte slice and a topic where the topic came from. It has some additional metadata that's not really relevant right now. But then we define two new small interfaces that we can use for ourselves. So these two interfaces are consumer and producer. The consumer interface has one method which accepts a context and returns a message, an ACK func, and an error. And then the producer has one method as well, which is similarly formatted. It accepts a context, an ACK func, so it can ACK upstream, and then a list of messages and returns an error. So this really helps us because it defines exactly what we depend on and what we need from this external package. So underneath this, we've implemented a Sarama implementation, an in-memory implementation, and finally, we were actually using NSQ for a long time, so we implemented an NSQ implementation. So not only did this help us with our testing regards, because we can use the in-memory implementation to be able to inject exactly what test data that we wanted to validate was, but it also allowed us to more easily move from NSQ to Kafka. And finally, I think it's a lot more understandable what we actually are doing with this package now. So why does this work? This works, once again, because consumers are now able to define exactly what they depend on. They can implement their own stubs, and it really greatly reduces the complexity if you're a library maintainer, if you don't actually have to export these interfaces. So don't take my word for this. People much smarter than me have blogged about this before. So Rakil, or JBD, a very prolific Go programmer, has written about this all the way back in 2014 on this post called Interface Pollution. And our own dear Bill Kennedy has also written about this back in 2016. And this idea is called interface pollution. So please go do some more research and figure out what works best for you. So next we're going to talk about my specific strategy when approaching testing. So my strategy is generally, I start with a very specific implementation and I test it. I don't worry about abstracting anything away. I will spin up servers locally using Docker, and I'll just test it against the actual implementation itself. Finally, when it comes time to it, I will find a need to abstract away that implementation. So at that point, I write a new interface, and then I write new implementations to satisfy that interface, and I refactor the tests to use that interface. Let's take a look at how that looks. So here we have a cache which takes a Redis pool, and we're embedding it directly. And this cache has two methods, get and set, just like any key value store would have. And importantly, in the get and set methods, notice that we're calling the Redis pool directly, and we're not doing any indirection whatsoever. So this is pretty simple, easy to understand. So when we go to test it, all we have to do is instantiate a new cache, passing in our Redis pool, pointing to localhost, and run our test as we would normally. Now, this is very simple and easy to understand, and the next programmer who comes along is not going to have any questions about what's going on. So This is a great place to start, and if you never have any other implementations and you're testing using Docker locally, there's no reason to change this. But say you want to switch to Memcache because it saves you money on AWS bill or something like that. So what you might do is you might abstract away this into an interface. So now cache accepts a store interface, and store is a fairly simple interface with just get and set once again. And then we, in our cache get and set methods now, we're calling into the store interface instead of calling into Redis. And then we write our new implementation for Memcache, which does the similar thing that satisfies the store interface and the methods that it has on it. And from there, we can actually refactor our tests so that we're not actually writing a new test. Instead, what we're doing now is we're injecting the specific implementations into the old test. So this way, this guarantees us the ability to know that when we're switching these implementations, it's actually going to match the behavior. So frequently, at least when I got started, what I would do instead is I would write these test cache Redis and test cache from Memcache. I'd highlight the entire code, I'd copy it and I'd paste it. But then you have issues with maintainability and code drift between the two tests themselves. By doing this and making sweet cache accept a testing.t and the interface that we actually, the implementation of store that we want to accept, we can run the same test against both implementations, and it gives us a high amount of confidence that both of them are going to work when we deploy them to production. So why would you do this? The main reason why you might do this is primarily to write less code, but also to be confident in the behavior that the behavior of both implementations when switching implementations. Most importantly, though, is that it communicates the intent of the dependencies that you depend on. It communicates to the next programmer, this is what we depend on in this package, and it makes it clear that those are the methods and the behavior that you expect from the package. Finally, let's get to a little bit more of a fun topic, which is the last HTTP test you'll ever have to write. So I can't personally take credits for this. I first saw this pattern presented at GopherCon 2017 by Florin. He's here at the conference as well, so if you have a chance, go speak to him. So what we have here is a new server which returns a basic serve mux. It has two handlers, which are just examples, of course. Both of the handlers have a check on the method and return some data. So this is fairly simple. We're just going to use this as an example. So when you go to test this, you might start by doing something like this, where you launch a Go routine to listen and serve on a single port, and you call new server. Then you run your assertions after doing HTTP GET on the particular return values that you expect. Now, this might work for basic needs, but it has some drawbacks. Primarily, you're binding to a port that you might have available or might not have available. Additionally, you're launching a Go routine that might never or will never close in this case. So this really isn't ideal for testing. So let me introduce the HTTP test package. So this is a standard library package that everybody should be using for their HTTP tests. And what it provides us is it provides two primary methods that really aid in testing our servers. The first method is the HTTP test new request method, which simply allows us to create a new request which is suitable for testing. And then the really beauty of this package is the new recorder method. So what this provides us is what it calls a response recorder. And what we can do with this is in the s.serve HTTP method, we pass it in as the response writer. So this recorder actually satisfies the HTTP response writer interface and allows us to be able to run assertions directly on that response after the code is run. So now we don't have to worry about binding to a particular port, and it's a lot easier to read this code and understand what it's doing as we maintain it going on. But that's not good enough. As any good Gopher knows, we should be using table-driven testing. So we can convert this test into a table-driven test. Notice how we had a lot of repeat code here. So when we convert it into a table-driven test, we simply have a list of tests cases that we want to run. We have the name, the method that we're going to run, the URL that we're going to hit, and then some expectations that we want to assert. So here we've re-implemented this test using the table-driven test. So we initialize the new server, we run through our tests, and we use subtests, t.run, to actually run each individual test, passing in the name, and doing the same flow that we did before. So here we're able to run our expectations, and everything's fine. Except for one problem. This relies on the fact that your server is completely stateless. So that's not really ideal. Let's say you want to test a login flow. If you want to be able to handle state like login, then you need to be able to handle things like cookies. So what you can do instead is in your test, you can actually initialize a new cookie jar, and in between each iteration of the test, you can apply all the cookies in the cookie jar to the request, and then after you receive the response, you can handle all of those cookies and set them for the particular domain of the request URL. And then as you're running your tests, you're actually able to test things like login and state transfer. So I use cookies in this example, but there's other examples that are useful as well. In particular, dealing with databases is always a challenge when testing. So one of my favorite features of Docker in particular is this feature that they have on most of the library databases. So for Postgres, for MySQL, they all have this special unique directory called docker-entrypoint-initdb.d. And what this allows you to do is if you copy all your migration files into this directory, when Docker spins up that server, it will run all of those scripts, all of those SQL scripts, to make sure that you have a well-defined schema before you even start your tests. Now, you could also copy in mock data here, but in my experience, I'd rather just do that in my tests. It just depends on what you're trying to do. So in your Docker Compose, you can simply say, use this Postgres, the context is local, and the Docker file is the Docker file PostgreSQL. So now in your test, you can actually initialize a new database pointing to that Postgres server that you spun up locally using Docker. You can initialize your server using that new database. And then as you're running your tests, it will have all the state transfer and allow you to be able to express very complex workflows in your table-driven test. So you can say login, click product, add to cart, checkout, and you can see all that happening inside your database in your table-driven test. So finally, not only can you do this for your server implementations, but you can also do this for your client implementations. If you have a rich client which has a lot of business logic or is doing some complex serialization, you can also use the HTTP test method to instantiate a new server which returns well-known data. So here I've created a table-driven test which does the same thing for client. It's a little bit contrived, but this is particularly useful if you're relying on some external party to use their API and they don't provide any means to test it for you. So if you're talking to the GitHub API, you can simply take a response, take the format from that response, and embed it right into that handler there. And then you can run through your rich client and actually apply the tests. So here we've got this HTTP client that we've initialized, which would actually be passed into some other more sophisticated client. Testing it the way I have here isn't super useful in particular. So I implore you all to go and look at the HTTP test package. It's got a lot of goodies in it. So to wrap up, testing is fundamentally about communication, and it should really be making your life easier. So if you're not, when you're testing, you just need to make sure that when the next person goes to read the tests, they really understand what the intent of the program was supposed to be. And finally, don't do anything without considering if it works in your environment. Engineering is fundamentally about trade-offs, and if we're not thinking about the code that we're writing, then we're really not doing our jobs. Thank you.
Okay, there are some questions.
With the example of the consumer package that you showed, where you implemented it in both Kafka and NSQ, and
yeah.
So this thing has interfaces, and I can imagine that you don't copy all this code through all your services that actually are a consumer, but you would rather share this. But then if you're, as soon as you make this like a library with the implementations for Kafka and NSQ, then you are exporting interfaces again.
That's correct. So this is a good example of when it was really valuable for us to be able to export this interface. This isn't something that, I mean, we might publish it eventually, but because we've really distilled down what it is that we're depending on in these various implementations, it really helped us. I think as a library author, if you're writing an implementation for a Q library, then you really shouldn't worry too much about exporting these interfaces because it's for a specific implementation. Does that make sense? It's like, it's a nuanced distinction that's hard to apply a rule to. In our case, we needed to be able to migrate between Kafka and NSQ easily, and all of the consumers needed to be in line with each other so that we could make that move.
Okay, any other question?
How do you deal with dropping of data for database? Like, do you expect the database has some state for each test and you have to reset it after each run?
I actually forgot to mention that. Right down here, I've got one small little method. It's truncate tables, where we pass in the test in the database. So yeah, you do have to make sure that you clean up the state in the database after every test if you're creating users or modifying it in any kind of way. Likewise, if you need to create state or fixtures in your database, you can do that before all the tests run. So.
Okay, any other question?
Thank you.
Thank you, Alan.